As an example, let us calculate the mean activity coefficient for NaCl in an aqueous solution at 25 degrees Celsius, where the solution is 0.020 molal in sodium chloride and 0.035 molal in calcium nitrate. To calculate the mean activity coefficient, we will be using the Debye-Huckel limiting law. So we first need to calculate the ionic strength of the solution. Let us not forget that all ions in solution must be accounted for in the calculation of the solution ionic strength. In the expression for the ionic strength, the first term is for the sodium ions, molality 0.02 and charge +1. The second term is for the chloride ions, molality 0.02 and charge -1. The third term is for the calcium ions, molality 0.035 and charge +2. The last term is for the nitrate ions, molality 0.070, since there are 2 moles of nitrate ions per mole of calcium nitrate, and charge -1. Do not forget to square the charges and multiply the sum by 0.5. The result of this calculation yields I is equal to 0.125. Next, we use the Debye-Huckel limiting law and write log base 10 of the mean activity coefficient equals minus 0.509 times the absolute value of the product of the charges for NaCl times the square root of the ionic strength. The result obtained is minus 0.17996. Make sure you use more significant figures than necessary so truncation errors do not affect the value of gamma plus minus. The last step of this calculation requires you to calculate gamma plus minus from log base 10 of gamma plus minus. To do this, simply calculate 10 to the power minus 0.17996, and you obtain gamma plus minus equals 0.661. As usual, remember that mean activity coefficients are always less than 1. On the previous 2 slides, we introduced the Debye-Huckel limiting law and demonstrated how to apply this law to the determination of the mean activity coefficient of an electrolyte in solution. However, we also indicated that this law is only expected to be valid in the limit of low ionic strength. To test this law, one can plot the log base 10 of the experimental mean activity coefficient as a function of the square root of the solution ionic strength. If the limiting law is applicable, a straight line passing through the origin and exhibiting a negative slope should be observed. Examination of the limiting law also suggests that the magnitude of this slope should increase with increasing ionic charges on the electrolyte. So a 1,1 electrolyte, such as sodium chloride, should exhibit a slope that is half the slope of a 1,2 electrolyte, such as zinc chloride, or a 2,1 electrolyte, such as sodium sulfate, and should have a slope that is a quarter the slope of a 2,2 electrolyte, such as copper sulfate. The theoretical limiting law is plotted for 1,1, 1,2, and 2,2 electrolytes. See the black straight lines. Experimental studies have shown that the measured mean activity coefficient, shown in the red curve, only follow the theoretical predictions of the Debye-Huckel limiting law at low ionic strength, typically for I less than about 5 10 to the minus 4 to 10 to the minus 3. A number of theories have been proposed for extending the Debye-Huckel limiting law to higher ionic strength. In this equation, A, B, and C are constants that can be found in tables in the chemical literature. Such an extended Debye-Huckel law can be used for solutions of ionic strength as high as 0.1.